So our quick look at the calendar. Today is February the 3rd. We just had our first quiz. Note that Project 1 is due on Monday. I think some of us have already finished. Maybe some of us haven't started yet, but I'd encourage you to get looking at it and give yourself a chance to check in with some of your classmates. Again, you're always welcome to work on the projects together. Today we talk about graphs and behavior of exponential functions. So let's give it a shot here at the bottom of page 19. And can we start in the back with tasks today? Could you read number 1? Okay, thank you. Kate. Thank you. Richard. Okay, so the very first World Series, there was a program that originally sold for a nickel, and there were probably hundreds of those programs sold back on that day in 1903. And then just recently, excuse me, one of the still existing copies sold for almost $250,000. And it turns out there are only 2 known copies from that original World Series, and one of them is in the Hall of Fame in Cooperstown, New York. And so when I read this back, month and a half ago, my initial thought was, well, was that a good investment? It's hard to know. Like, it looks really good, right? Going from a nickel to $250,000, but we also waited 100 plus years to get that investment. So the question I had is, what was the growth rate? Like, I could put my money in maybe a certificate of deposit right now and get 4 or 5% interest, and I wanted to know what is this as an investment. So that's where we start today. So let's go ahead and think about this formula right here. We're going to treat it like an exponential growth kind of thing, like an investing in the bank thing. And we've got some data in here. And so we're going to translate this data into points. And so maybe the first column will be years, and then the second column will be value. And what's the first year that we have information about? 1903, and what was the value in 1903? It was 5 cents. So I'm going to put 0.05. And then the other year that we have, 2011, that's when this thing was sold at auction. And its worth was $241,500. And do you guys see that we've got a couple of points that we can just plug into our exponential functions up above? And do you remember that when you use 2 points to find an exponential function, there's an easy version if you have it. There's a certain gift that you might be given, and then there was the hard version, which required a complex technique. What was the gift that we're hoping to be given? Was a 0. If you happen to have if t is 0 and you know the y value, that's a gift, because that is a. That's the value of a, right? At time t equals 0. Okay, so 1903 I would not say is a gift unless we define it to be a gift. Are we obligated to call it 1903? No, let's change it. What should we call it? 0. Let's do years since 1903. So we update years since 1903, which means we have a gift. 100, how much? 108. Okay, you guys have 2 points now. One of them is the gift, and the other one you'll do a little work on. Check with your neighbors and see if you can't find the formula. Again, you're plugging into an equation of that form. So that's the 108th root of this number, the 241,500. Do I need parentheses? I need parentheses. Parentheses. 241,500 divided by 0.05. Is this going to work? Oh, good. Okay, so that's B. I feel like when I tried this on my calculator at home, it gave me an error. Like it wouldn't do the 108th root. Anybody have problems with this? You could also do to the 1 over 108. Yes. Because here, on the I don't know where we are anymore. On the calculators here, so you type in the root that you want, 108 first, and then inside of math, it's number 5. That x radical means any old root that you want. Okay, so B is this 1.153. So let's get that here. 1.153. So that means that, the formula that we end up with here is P of T is the nickel, 0.05 times 1.153 to the T. So you want to know how much it's worth at any moment in time, you plug into that formula. Can you guys look at that and tell me what interest rate, like if I'm thinking of it as an investment, do you see the interest rate from there? Do you see it's the 15%? And so I'll write this formula that I mentioned the other day. But this is our second time kind of seeing it. Like, you know what B is, but it turns out that B is always 1 plus the interest rate. B is always 1 plus the interest rate. So that 1.153 means that if you subtract 1 from both sides, you get the interest rate, which is 0.153, 15.3%. So this thing grew as an investment, it grew at a rate of 15.3%, assuming it was always growing at the same rate. So what's that? Should have bought 4 of them, right? 20 cents, but then we're at $1 million at the end of this. So so that looks like a quite healthy rate of investment. Yeah, same idea with comic books. Yeah. So good questions to ask about what's the growth rate. Right. Yeah, there's definitely a supply kind of thing here. Yeah. Yeah. Okay, so we'll go to the next page. Assuming the growth rate that we just found, can you guys check with your neighbors to figure out what the program would have sold for if instead of waiting until last year, this owner sold it in 1973? Okay, so selling in 1973, we have to first find what value of T is that. That was 70 for our definition, and then we plug into the formula and we get about $1,000. And so, yeah, it sure seemed like, like waiting. Let's see, so from 1970 until last year, that's 41 years. So in the first 70 years, it gained about $1,000. In the next 40 years, it gained about $240,000, right? And so, and this is what happens when you compound, is that the bigger the thing is, the more interest you get on it. And so most of the growth was in the last few decades. One little thing, I don't know how you guys typed this into the calculator. Perhaps we just typed it in as I've written it there, the 0.01 or 0.05 times the 1.153 to the 70. And I will encourage you, part of what I want to accomplish in this course is to make it so that we can get the most accurate answers the calculator can possibly give us. And I have rounded, right? That 1.153 that I retyped was a rounded number. The correct number was this number that's right at the top. So I don't know how much difference it will make, but again, I want us to use the calculator to its fullest. So if you have this number already typed into your calculator, and anytime you want to go back to something you've typed in before, just hit second entry a few times and it'll give you things that you have typed. So that is the number that I found before. It is still 1.153, but now that it's there, what can I raise it to? I can raise it to the 70th in its current form, to the 70. To the 70, and then times the 0.05. How different was it? It was $10. Okay, so $10 is not that big a deal, but I mean, like you guys, it was okay. But anyway, that's the kind of, like, that's rounding error, right? If you retype numbers, you are creating error where there doesn't need to be any. So use the calculator to its fullest, and ask me, anytime you're not sure, how do we use the calculator and all of its digits? Yeah, Todd. Yeah, this is another way to do it. So let's take a look at that. Storing is a real nice feature that a lot of folks don't end up using. So again, I'm getting back to that number, 1.153. That is B. There's this little button over here that says STOW. It stands for store. And if you hit it, and then you type in one of these green letters, so I got to hit the alpha button to get to the green letters. I'm going to choose B because that's the name of that thing. Now, anytime I ask it how much B is, it knows that number, plus some digits that it's not even showing us. It knows more than it's showing us. So if I were to type in 0.05B to the 70, 0.05 alpha B raised to the 70, then it should give me the same $1,074 that we got before. So it's a very nice ability to store up to 26 different numbers. And B will remain in the calculator as 1.153 until I ask it to call something else B. Good, thank you, Todd. All right, let's go to number 2, and I think we're up to Emily. Okay, let's go to Todd. Okay, go ahead. 2 sketches and 2 equations. There are lots of different equations you could come up with. Okay, so we've got 2 graphs. One is rising, the other is falling. And the only difference between these is the value of B. What kind of a B do you have for exponential growth? Greater than 1. 1 is the magic cutoff. If you keep multiplying by a number bigger than 1, you get bigger and bigger and bigger. If you multiply by a number less than 1, like 0.8 or 0.7, you get smaller, smaller, smaller. One little technical detail, we always insist that B is bigger than what number? Yeah, negative B's lead to all kinds of problems, so we don't even talk about them. Okay, next part here, it says each of the graphs above has a horizontal asymptote. What is the horizontal asymptote for each graph? Yeah, there's a 0 in the answer. So remember a horizontal asymptote, I said remember, or maybe you haven't seen it before. A horizontal asymptote is a horizontal line that the graph gets very, very close to. And in this case, for the first picture, if you go to the far left, the graph here gets closer and closer to what horizontal line? The x-axis, which is y equals 0. And on the other graph, as you go to the far right, what does the graph get closer to? Same thing, still getting closer to the x-axis. So those 2 things are called horizontal asymptotes. So in this case, the graph, each of them has a horizontal asymptote at the x-axis, also known as the equation y equals 0. Okay, so we'll go to 3 for Sam. Okay. So I'm actually going to pause you right there. I don't like that sentence there, so just cross it off. We're not going to do it. But if we take a look at this this picture above, and we kind of try to refer one of these things to this thing that Sam just read, those funny symbols mean something very specific for one of these graphs. It means that as x goes to positive infinity, can everybody point? Which way is that? X going to positive infinity is out here to the right. F of x is going to 0. It says equals 0. Technically, it's never quite 0, but it goes to 0. Which one of these things has that property? That when you go to the right, the f of x values approach 0. It's this one on the right-hand side. And again, as as x goes to infinity, these y values are getting very close to 0. And that thing in the red circle is how we write that, okay? So what I'd really like you guys to try is the next part, number 4, and we'll go to Melissa. Yeah, what's the difference? Okay, so see if you guys can kind of piece together, for each of those graphs, you're going to have 2 different limits that you're finding. Use the notation, see if you can understand what the things are equal to. So yeah, so give that a shot and check with your neighbors. Okay, so let's come back together and see how we're doing here. It's a lot of symbols. It looks like gobbledygook until you're able to parse through it. So if you didn't make a lot of progress on that, no worries. We'll understand it with practice. I've redrawn my 2 graphs down below just so we can see them on the screen. And for the first graph, the one on the left, these first symbols here say limit as x goes to infinity of f of x. So there's my function. X going to infinity is always to the right. And the question is, what happens on this graph when x goes to the right? What happens to the y values? They get bigger and bigger and bigger, right? As you trace this guy, x going to the right, the y values get bigger and bigger and bigger, infinitely big. And so the answer up there is infinity. That's heading up forever. Other questions on that first part? Okay, same graph, but now we're going to send x to negative infinity, which is always going to the left forever. And if you trace this guy to the left forever, what happens to the y values? They approach 0. And so that limit is equal to 0. And again, it never gets to 0. So it looks very funny to say f of x equals 0, but that's not what we're saying. This notation means it gets very close to 0. May not ever actually get there. Now for the right-hand graph, same kind of idea. As x goes to infinity, that means run to the right. What happens to the y values? We approach 0. And then for the last limit, as x goes to minus infinity, which is to the left, what happens to the y values? Approaches infinity. Other questions on that? Like I said, the notation seems unwieldy in the beginning, but with practice, it becomes wieldy. Okay, let's go to the next page. Okay, number 5. I think we're up to Topher. Okay, and you don't have to read all the symbols, but in part A, there's a couple of limits I want your graph to satisfy, and then in part B, different ones. So see if you can come up with some graph that satisfies, 2 different graphs that satisfy those. Okay, so for the first one, it says limit as x goes to infinity is 2, which means as you run to the right, you have to get closer and closer to this horizontal line at 2. So for example, I can do something like that. And the limit as x goes to minus infinity is also minus infinity, which means at some point what needs to happen to this graph that's started? It needs to eventually go down. So let's eventually make it go down. Lots of different answers are possible. All you need to do is at the right-hand side, get close to 2, and at the left-hand side, go down to minus infinity, and in between, anything you want. And I know that some folks don't like that a graph hits the horizontal asymptote. Somewhere along the line, we have been told that graphs can never hit their horizontal asymptotes. This is false. Here's an example of a graph that hits its horizontal asymptote. Okay, they are allowed to hit. Many times they never hit, but they are perfectly allowed to hit horizontal asymptotes. Okay. Oh, you could hit it on the right-hand side too. You could make it hit a few times and just get close to 2 on the right-hand side. Anything you want. Okay, same idea with this other one. We're supposed to go to -4 when you go to the right, so something like that, and then 3 when you go left, so something like that, and then we won't do anything crazy in the middle. We'll just kind of connect them. And you know, to date, it seems like we don't have any like actual formulas that we know of that have 2 horizontal asymptotes. But it turns out that there is one that we will see later on in the semester. I'm going to give you guys an opportunity to earn a little extra credit. This is very rare. You can ask my students. Um, so here is a function that has two horizontal asymptotes, kind of like the one that I just drew here on the right. We will talk about this sin, cos, and tan business here in the middle. But if you do the second one, yellow, and then tan, it comes up with that funny tan to the -1 business. And if you hit an x, then it's going to graph this thing that we will call inverse tangent of x. We'll do that in like a month and a half or something. But if you just graph that on the standard window, I think that, what happened there? Let's go back. Delete, zoom, 6. We will see a graph that has two horizontal asymptotes. One at the far right, a different one at the far left. I will tell you what those numbers are. And once I do, here's where you can earn some extra credit. See if you can think about how to tweak that equation, which you don't have to know what that equation even means, but just know that the graph of that, whatever it is, looks like this. Can you tweak this equation to make a graph that looks like this? I want my graph to go to 3 on the far right and -4 on the far left. So in order to do that, you need to know what the current graph does. And I will tell you that the horizontal asymptote of this graph is pi/2. And on the bottom, it is -pi/2. Okay? So extra credit if between now and Monday you can come up with some equation to turn that graph into the one that's behind. All right? Pi/2 and -pi/2. I will give you like a free homework kind of thing. Any questions on the extra credit? Something like that. Yeah, make sure it goes up to 3. Yeah, so normally it's pi/2 and -pi/2. You need to do something to the equation in order to change it. Okay, let's move on. We'll go to number 6. Who's our reader now? Is it Kelsey? So annually they both pay 12% interest. So it feels like we're talking about the same thing, but one of these is decidedly better for us, the person investing. Which one is better for us? The second one. Getting 1% every month, it turns out, is better than getting 12% once at the end of the year, because the interest that you earn at the end of the first month then gets interest in the second month, and then that interest gets interest in the third month. And that's the idea of compounding. On the one hand, compounding is great for us, the investor. On the other hand, if you own a car or a house and you are paying loan payments on either of those things, then you are getting hurt by compound interest. It's the same idea as the bank account, just the roles are reversed. The bank has lent you money to pay for that car or the house, and you are paying them back. But you are paying them back with this kind of monthly compounding. Okay, number 7 is a formula that I think we have seen before. We're just going to use it. We're not going to read all the symbols and what they mean. I think we've seen it before. So we're going to jump down to 8 for Chris.
At 12% interest compounded monthly, how much would $1,000 grow in 10 years? How long would it take to grow $5,000?
Okay, so let's give this a shot. We're going to use this formula, and we're going to plug in all the different pieces. So I know that the P in the formula stands for what? That's the principal. Which one of those numbers is the principal? That's the 1,000. And then we go 1 plus R. R is the interest rate. What is it here? It's 0.12. Make sure you convert percentages into decimals whenever you use these formulas. So it's 0.12 divided by. And then we get to N. N is kind of the funny thing. N is how many times you compound every year. So if we get interest compounded monthly, the question is really saying how many months are in a year. And in this case, it's also 12. Raised to the, it's the same N up there as it is in the bottom, so it is still 12. And then finally, T is how many years you wait. And in this example, 10 years. So if you carefully type all that into your calculator, then you will find how much your $1,000 grows to. Okay, I got $11,000. Is that right? No? Yeah, so I made a mistake that's really easy to make because this 12 times 10, when I write it, does not require parentheses. But that's because I can write it up there, and every one of you can see it up there. Calculator can't see that. So what I need to do is put parentheses around this whole power. That's how we need to type it. Really sneaky, because you need parentheses on the calculator when sometimes you don't need them when you write it. Okay, 3,300. All right. So we got 3,300 and what was it, 38 cents? 38, 39 cents. All right. Okay. And then the follow-up question says, how long would it take to grow to $5,000? So same kind of setup, but in this case, we know A. A is the future amount, the one you want. It's 5,000 bucks. Everything else is the same, but what's the unknown now? Is T. We need to figure out how long it takes. So instead of 12 times 10, it's a 12 times T, some unknown time. We are. So for some of you, you are probably quite comfortable with logs and solving this equation using this idea of a logarithm. Officially, we are going to review logs in the coming classes, so I'm just going to pause here and say, together, we don't have the tool to solve that equation, but we'll see it soon enough. Certainly, you could use your graphing calculator to intersect these two things and find the point of intersection. So solving that one is pending, we'll say. But some of you may already be quite comfortable solving it right now. Okay, let's go to the next page. And we'll go to number 9. And we're up to Allie. Okay, so go ahead. Okay, so you can see I've graffitied up this one too. So cross off that 1% business. I'm changing it to something equivalent. I just didn't like the way I had phrased it before. So 12% annual interest compounded monthly. What does that work out to each month? 1%. So it's the same, right? It's just 1% a month, but I wanted to be able to talk about them both as being 12%. Just the difference is how often we get interest. Okay, so the first thing Allie read was all this gobbledygook about nominal rate and effective rate. And if you go to a bank, you'll actually see those phrases. So the nominal rate is well, I mean, maybe you know NOM. What does it generally mean, like as a prefix? Nom.
Is that why there was like 2 interest rates? Pick up the money.
Yeah. Yes, so you're going to see two things. You'll see an APR is the smaller number, and then this APY a little bit bigger, and that's exactly what we're going to talk about here. Nom generally refers to a name. So like if you've seen like an author's name written as a nom de plume, it's like the name that they go by when they're writing. So nominal means the rate in name only. So for both of these problems, in name, the interest is 12% annually. But for the one that's compounded monthly, that's not really true, right? You end up getting more than 12% when all is said and done at the end of the year. So for both of these guys, the nominal rate is 12%. It's like, what is it named to be? Ignoring the fact that it's compounded however often. So this guy here kind of ignores compounding. For the effective rate, Well, let's see. The one that pays 12% interest once a year pays 12% interest at the end of the year. The effective rate is simply 12%. You don't get anything more. It's just on the surface. It is what it is. But the effective rate for this other one is going to be higher. Maybe it's like 12.4% interest. Here's the goal. Suppose that you were to invest some money at this 12% compounded monthly. What I'd really like to know is how much will you have at the end of the year? Will you have 12.4%? Will you have 13%? You're going to have something. And so we're going to kind of pretend that instead of getting interest once a month, we're just going to give you all the interest at the end of the year, and it's going to be more than 12%. What we're after is what that number is. Is it clear what we're trying to get here? Okay, well, let's do some stuff with numbers, and we're going to see what it is. So here's the basic idea. What you want to do is think about the formula that, so annual percentage yield. The formula that we just used was this thing with the P and the 1 plus R over N to the NT. To make life easy, let's pretend we're investing $1. Which one of those is 1? That's P. So 1 times 1 plus, okay, for this example, what's R? It's 0.12, make sure we write it as a decimal. Divided by N, the number of times you compound every year, 12. Raised to the same N. But if I want to figure out what the interest is like for the end of a full year, then how much is T? It's 1. So this is what we're typing into the calculator. We're pretending we invest $1 for 1 year, and we're going to find out what it really grows to. What do we get at the end of the year for our dollar? $1.126. $1.127. Okay, 127. What did we get? Second enter. And that 1 plus needs to be in the parentheses. Okay, we get 1.127. Okay, so what does that mean? Well, if your dollar was getting just flat 12% once at the end of the year, how much would your dollar have grown to? $1.12, right? That you'd get 12% interest on your dollar. So you would have $1.12. But we had a little more than $1.12. And that extra 0.7 of a cent is the effect of getting interest not just once at the end of the year, but getting a little bit of interest every month. So that that really means what percentage interest have we gotten? Do you see the 12.7? It's the same kind of like extra stuff like for the baseball program question. Yes, you're paying the higher one if you're paying something. Okay, so then how do we fix it? Well, we're going to subtract 1 just like we subtracted 1 with the baseball example. So I'm going to put a subtract 1 in the formula over there as well. So then the actual interest that we get here is 0.127 or 12.7%. So that is the where is it? Nominal. That is the effective interest rate, 12.7%. On the surface, it looks like 12%. And by virtue of getting it monthly, it's really 12.7%. What about advertising? Yeah, they'll show you the one that makes it look better for them, depending on whether you're investing or whether you're borrowing. Because, yeah. Okay, so that is the annual percentage yield or the effective interest rate. Other questions on that? So I've included the formula. I mean, I'm not a fan of just like memorizing formulas. I was a fan of using this formula at the top that we know and pretending we have $1 invested for 1 year and realizing, oh, it didn't just get to $1.12, it got to a little more. And that little more must be, you know, because of the compounding. But if you're a formula person, there it is. Okay, group work is down here. There's an exponential model here, and I think another on the next page. And presumably there are answers somewhere as well. So see how far you guys can get in 12 or 13 minutes.